We are in Chapter 4, Introduction to Dynamic Models. In this video, I am going to explain dynamical systems. It is the section 4.2 in our textbook. Now, dynamical system models are the most commonly used type of dynamic model. In a dynamical system model, the forces of change are represented by differential equations. In this section, we will focus on the graphical method for obtaining qualitative information about a dynamical system. Okay, so let me explain the example. It is example 4.2, the page number 121. The blue whale and fin whale are two similar species that inhabit the same areas and are thought to compete. The growth rate of each species is estimated at 5% per year for the blue whale and 8% per year for the fin whale. The environmental carrying capacity is estimated at 150,000 blue whales and 400,000 fin whales. The extent to which the whales compete is unknown. In the last 100 years, intense harvesting has reduced the whale population to around 5,000 blues and 70,000 fins. Will the blue whale become extinct? We are going to follow the 5-step method. As we know, the first step, we should define our variables and assumptions, then objective. I use B, number of blue whales, and F, number of fin whales. GB and GF, growth rate of blue whales and fin whale population respectively. CB and CF, effect of competition on blue whales and fin whales respectively. Now, assumptions. Before I explain the assumptions of the example, let me give an equation. We use this equation for the growth rate of population P equal Rp times 1 minus P over K. So R is the rate at which the population would keep growing in an unlimited environment. Right, and K is the maximum number of individuals that the given environment can support. The maximum number of individuals that the given environment can support. Okay, we need this equation for this example. We use GB for the growth rate of blue whales population. So let me write down an equation for this. So according to the above equation, our R equal 5%. You see in the example, the intrinsic growth rate of each species is estimated at 5% per year. So therefore R equal 5%, which is 0.05, and K, for this case, it's explained the example, the environmental carrying capacity is estimated at 150,000 blues. Okay, 150,000 is the K. So now you can plug these numbers. So 0.05. So P, we use here B, the blue whales population. Therefore I will use B over here. Then 1 minus B divided by 150,000. So same thing we can write down for the GF for the fin whales. This one 8%. Please read the example again. It say 8%, which is 0.08. Then F 1 minus F, what is the maximum? 400,000. Therefore 400,000. So these are the two assumptions. And also CB, effect of competition on blue whales. So and the fin whales, both must be equal. So we can write down, I use the alpha, is the just a positive real constant. So we can write down alpha times BF. So you know very clearly B greater than equal 0 and F greater than equal 0. Okay. Then objective. Determine whether dynamic system can reach stable equilibrium starting from B equal 5,000, F equal 70,000. Now step 2. Step 2 is to select the modeling approach. We will model this problem as a dynamical system. So like last time, we consider n state variables. Then we do have functions f1 to fn represent the rate of change. So I will write down same function f1, x1, xn. This f1 is the rate of change of variable x1. Therefore you can write down dx1 over dt, rate of change of the variable x1. Similarly you can write down up to n dxn over dt, fn x1 xn, n differential equation, actually a system of differential equation. So you know x1 xn is in S. S is a subset of Rn. You can write down the point x, x1 xn, fx equal f1x fnx. Then the dynamical system equation can be written dx over dt equal fx, which is f1x fnx. The points where fx equals 0 are the equilibria, and we will pay special attention to the vector field nearby these points. I will explain this in step 3. So step 3 is to formulate the model. As last time we used x1 equal b and x2 equal f. Then we can write down the functions x1 prime equal f1, x1, x2. f1 represents the rate of change of x1. According to our assumptions, you can write down f1 gb minus cb. Once we plug the x1 and x2, gb can be written 0.05 x1 1 minus x1 divided by 150,000. You can write the CB alpha x1 x2. x2 prime, which is f2 x1 x2, can be written gf minus cf. So equation should be 0.08 x2 1 minus x2 divided by 400,000 minus alpha x1 x2. So you know the state space, which is S, equal x1 x2, because we do have only two variables, x1 greater than equals 0, x2 greater than equals 0. So next, step 4, which is to solve the model. So how do we solve model? As I mentioned before, we use the graphical method. Let me draw the graph of pinwheel versus blue whales. So x2 versus x1. If you consider the graph f1 equals 0 and f2 equals 0, you can get two graphs like this. So you see, we should consider 4 points here. This 0, 0. So you can find this one 150,000, 0, 0, 400,000. This one depend on our alpha. Step 4 and step 5 are explained very clearly of the textbook, the page number 123 and 124. They explain also sensitivity analysis for this example. So please read 123, 124 and 125 pages to understand these steps.